Welcome, everybody, to Deep Impact, Optimizing Outer Wilds for the New Platform. Firstly, a couple of introductions. My name is Gustavo Castro. Everybody calls me Gus, so please do so. I am a senior software engineer at Unity. I've been at Unity now for, I think, 8 years. And in total, I've been in the industry for about 12. Yeah.
And hi, I'm Raz. My full name is Razvan Luta. I've been at Unity for about 6 years, and I've been in the games industry for about 13 years. And as you can see, half of that has been at Unity. I've worked in games across a variety of platforms, from mobile and web development all the way to high-end consoles and PCs. And I'm also based in San Francisco in California, just as Gus. So, right, now with the introductions out of the way, let's talk a bit about our agenda for today. Gus is going to tell you a bit about our team, what our team does at Unity. And then we'll start with the main part of the presentation that you're all here for. Right? We're going to talk about our goals and objectives. What did we set out to do when we started on this project? We're going to talk about some of the challenges that we encountered along the way. We'll talk about the solutions, the systems that we built to solve these problems. And then we'll end with a few conclusions and some takeaways that we took, and also that you could take and apply to your projects. All right, so I'll pass it back to Gus so he can talk about our team.
Right. So what do Raz and I do at Unity? We're part of a team that does that provides specialized development services for our customers. So this takes the form of targeted optimizations, where some of our team members will go in, take a look at your projects, and either implement or provide guidance on how to best optimize, or where the best performance gains can be found. And then the other two very common services that we provide are custom development and co-development. Custom development being you provide us with a task or features that you want implemented in your project, and we go in to deliver those in a timely manner. Co-development is where we spin up a team and then work alongside your team to work on your project and deliver features and deliver features. The second thing that our team does, our team does, is provide feedback directly to our engine and services teams. We gain experience from working with you all, and direct feedback back to the engine.
Right, so as Gus mentioned, a lot of what we do is the type of work called professional services. But building on that explanation that Gus provided, we just wanted to show you a few of the partners that we worked with in the past and some of the games that we helped with. On top of that, as Gus mentioned, a large portion of our work is these types of professional services. So you may ask yourselves, how do we pick these partners, and how do we find these perfect partners to work with? Well, we usually try to solve difficult problems, right? We want to help you figure out things that you would need help with. And also, we try to solve the difficult problems that are about the Unity engine and about the Unity ecosystem and the Unity editor, because we think that we are the Unity experts and we can provide that expertise to you. At the same time, we try to solve these challenges, not just for you, but things that we can take and apply as learnings and even improve the product for the entire Unity community. That's ultimately our goal, like Gus mentioned, to bring that feedback back to the Unity editor and engine teams. And lastly, we also look for projects that can help push the Unity engine further, right? So we look for projects that can be a test bed for the newest, most cutting edge of what Unity can offer.
All right, with intros done, let's move on to some of the meat of this presentation. First, and very obligatory for Outer Wilds, this is a spoiler warning. So if you haven't played Outer Wilds, just know that we are going to spoil some content, because we wouldn't be able to talk about Outer Wilds without talking about Outer Wilds. All right, so let's get started. Outer Wilds is a knowledge-based game where the player, you, find yourself stuck in a time loop. The game is developed by Mobius Digital and published by Annapurna Interactive. And I suppose the goal of the game really is to figure out why you're in a time loop and get yourself out of it. And you do this by exploring the solar system that you exist in, that you play in, right? And you go looking for clues left behind by an ancient civilization. Yeah, the solar system is made up of very unique planets, very different from each other, each with its own challenges to the player and to development.
Right, so let's talk a bit about our objectives. Now that you understand a bit about the game, let's see what our goals were and what did we set out to do on this project. So together with Mobius and Annapurna, we wanted to bring this game to the Nintendo Switch. Right, bringing this game to the Nintendo Switch meant bringing this game to an entire new audience on completely different hardware. So we wanted to do this while delighting players with the same experience, and most importantly, to try to keep the core of the game intact. We wanted to have the same inviting vistas and scenic views like you see here, maintain the physically accurate simulation as close as possible to how it was on the original experience on PC, and keep all the subtle storytelling and narrative moments that you have in the game. All right, so building from the goals, what were our challenges? What did we try to overcome when we started building this project? Well, first, as you've heard up until now, this is built for completely new hardware. While the game performed really well on the original platform, on PC, when bringing it to the Nintendo Switch, we encountered some challenges, right? We wanted to streamline how certain parts of the game worked and how some of the systems were built so that we could optimize the Nintendo Switch experience. At the same time, we wanted to bring this game to life without compromising any of the experience. So starting on that, we hit 3 major bottlenecks: the memory usage, the GPU performance, and the CPU performance. At the same time, one other challenge, more meta, was the the parallel development. What I mean by that really is, while we were developing the Nintendo Switch version of the game, the Mobius team, the Mobius Digital team, the original builders of this game, were working on the DLC. So what that meant for us was that we had to work downstream from them and be able to keep taking the changes that they made. So in the next couple of slides, we'll be talking about how we built these systems so that we can keep taking the input and changes from them and re-output optimized content. So be able to be flexible like that. All right, I'll pass it back to Gus.
Right. So those were the initial challenges. A couple of project logistics that we needed to get out of the way at the beginning of the project were, one, we were working the project was in Unity 2017, and we decided to upgrade to 2019. Why? Mostly just to make sure that we didn't have to continually upgrade to keep up with SDK requirements. So better to do that early and make sure that we have a nice long runway for release. The second thing we did was re-implement input in the game. This was for many reasons, but ultimately we re-implemented it using the new Unity input system, and Mobius Digital was able to adopt both of those changes, and were able to release the game on multiple platforms with these new implementations, or with these changes. Yeah. And lastly, we swapped to Unity version control simply for iteration time, to improve iteration time on our team, and to also mitigate the risks of, like, we were about to generate a ton of content with what Raz is going to be talking about in a few short minutes. Another challenge was the design of the game. As many people in the community know, the game actually runs on physics simulation. The solar system is running with physics, with a total physics simulation running. That is to say that the planets are not running on rails. If you take your ship and ram it into a planet, it does actually have an effect. Minuscule as it might be, but it exists. And honestly, I think you can push a moon out of the way. Another thing that one of the bigger challenges that we also encountered was the mesh density. I know Outer Wilds may not look it, but it is a vertex heavy. It has dense vertex counts and lighting and content.
All right, so now that you understand a bit more about the framework, about what we tried to do and what our challenges were, let's talk a bit about the solutions. So what are ultimately the systems that we put together to help solve these problems? So systemically, we had two major additions, the asset processing pipeline and the custom occlusion system. And we also made a few other major optimizations that didn't necessarily fit into those two buckets. So I'll be talking about the asset processing pipeline, which can be quickly summarized as a linear set of steps that get applied on a scene that output a new optimized scene. And over time, we essentially kept adding and adding to that system. And what that allowed us to do is, like I said earlier, take some of the content that came updated from the Mobius team, put it through the process, and output a new reduced scene. And then I'll let Gus talk a bit about the custom occlusion system.
Yeah, because the design of the game is very dynamic, the planets move at all times, we found that the occlusion system, we couldn't use the regular out-of-the-box occlusion systems because they all rely on static data. So we needed to come up with a custom occlusion system that could handle that, that could be dynamic, but also be efficient enough to run in this game. So we ended up using a combination of jobs and burst to get that accomplished.
All right. So the first major system, the asset processing pipeline. Why do we need this? As I mentioned, we needed a way to be able to apply these optimization, verify and validate our gains, and then also keep taking changes from the Mobius team to be able to continue to iterate and get the latest updates from the DLC without changing the original context. That was the most important part, and this was one of our solutions. In the next couple of minutes, I'm going to be talking about each of the major individual steps that we had in the asset processing pipeline. So first, collider swapping or collider optimization. Why we had to do this? Well, the main goal here was optimizing CPU performance. Essentially, what I mean by collider swapping is that we try to do a few tiers of optimization. One, you can see in the image on the top, is to simplify complex mesh colliders. So we start with the mesh collider, we end with the mesh collider, but a much more simplified one that still maintains the same gameplay feel, but is using far fewer resources. The second type of collider optimization is replacing mesh colliders with primitive colliders, may that be one or several. The important thing to note here is that typically a single mesh collider is still more expensive on the CPU than several simple colliders, right? Several primitive colliders. In our case, I want to show an example here going from a very low poly mesh collider to a box primitive collider, right? And that in itself is an optimization. This, you see, it doesn't change the gameplay too much, especially in a fast-moving game, but it is a performance improvement. And last but not least, reducing just the number of unique colliders. Essentially, what we tried to do here is take colliders where they were kit bashed together and try to simplify them in larger, simple shapes, where that was complex mesh colliders or just simple primitive colliders, just reducing the overall number. The next step in the reduction pipeline that I want to talk about is the mesh swapping. So one important thing here is to note that our objective here was to primarily reduce memory usage, but also we had some GPU gains with this. Our main objective was to reduce vertex count close to the player. So what I mean by that is essentially think about it as LOD 0 optimization. One of the unique challenges and why we had to do a mesh swapping approach as opposed to typical mesh optimization was because we needed to maintain the game object hierarchy intact. There are several systems in the game that rely on the game objects being in a certain place in the hierarchy and having certain data attached to them, right? Different Unity components or custom components. So what we did then is built a system that allowed us to index all the unique mesh references and then have a counterpart of a reduced mesh that we created either through manual or automatic ways, which we'll talk about in a bit, and then swap the two every time. So it would look for a mesh reference in the scene, find every single object that would use that mesh, and replace it with the optimized one. Let me show you here a before and after. I'll get the bit out of the way. So this is, for example, if you take a look at the planks, these are more high poly and more complex. And then in the updated version, after we swap the meshes, it's a more simplified one. And this is a piece of optimization that we did with the help of the Mobius team, for example. So I'll be going back and forth a few times just so you can see the difference. And the important thing to note is the plank is what I'm showing you here. The planks are what I'm showing you here. But this optimization was applied to a lot of assets in this way. All right. Next step, shader optimization. So why do we do this? Of course, this one's pretty straightforward. We did it to improve GPU performance. What we tried to do is create essentially an optimized version of the shader. And we did this through a few different ways. The one example that you see here is a simplified version of the standard shader. And in our case, we removed some of the things that didn't make a big visual impact, right? We tried to reduce the amount of texture reads. We tried to reduce the complexity of the shader by removing normal maps in some cases. I think this one's an example. Yeah, this one is an example where we removed normal maps. And it didn't make a big enough visual impact, and it was a really good performance optimization. So similarly to the mesh swapping process, for the material swapping and for the shader swapping, what we did is kept an indexed list of all the materials being used and replaced each one of those materials with a counterpart that was using the optimized version of the shader. Next is the particle optimization. This is another piece of the reduction pipeline that runs automatically, and it was another one intended to help GPU performance. One of the great things about this is when using the Shuriken system in Unity, all these optimization benefit the CPU as well. So the 3 tiers of optimizations that I like to think of that we did here are one, just general project level optimization. So what I mean by that is we try to look and make an educated guess on a maximum cap of particles per particle system. And this was, again, an automated process that was running every time on the scenes as we got them. The second tier of that was scene level macro optimization. So on top of the project level maximums, we tried for each scene to find an appropriate percentage amount reduction just for the count of particles on each particle system. And lastly, the more specific ones were just targeting super specific particle systems, like the one you see in the image behind me, to do optimization. So in this one in particular, if you're familiar with the game, this is something that the player can interact with and transport them from point A to point B. And this is also a particle system that is used all over the game. So optimizing just this one in particular had big benefits because it was used in many places. So in this case, for example, we optimized this by reducing some of the custom vertex data, and also, and that's the process that does the undulation, and also reducing some of the custom texture reads and the shader complexity. And another awesome part with this is that this was also something that the Mobius team helped us optimize because they really cared about the look of this, right? This is something that's gameplay critical, and they wanted this to feel very similar, if not identical, to how it feels in other parts of the game and on other platforms. Next in the reduction pipeline was the lighting optimization. And this was another optimization that we did primarily for GPU optimization purposes, but also helped the CPU quite a bit. You can think of this in 3 tiers as well. We first tried to do an overall light count reduction. Essentially, the game is very big, and it has a lot of unique lights. So what we tried to do is look at lights that did not make a big visual impact and didn't change the gameplay too much. So we looked at lights that had either a short range or very low intensity that the player would not notice if they didn't exist there. Right? So this is a bit brute force. But the second step was light consolidation. So what I mean by that is we looked at areas where there were many point lights that were contributing to the visual of the scene and tried to combine those all in a single light that achieved the same effect, even if that meant that it needed a slightly larger range or a bit more intensity. And what that did is reduced the amount of loops that the CPU would need to go through to pass this information to the GPU. And that improved CPU performance. And then last but not least, shadow casting optimization. So what I mean by this is that we tried to find lights that were casting shadows but didn't really benefit from casting shadows, where it wasn't visible, right? So very brightly lit scenes where a small light with a low intensity didn't necessarily create the visible effect when casting shadows. So I want to kind of show you a counterexample to that, just to prove this point. If you see this point light on top of the fire here, this is one that was very gameplay critical and also a storytelling moment. So this is an example of a light that we couldn't turn shadows off, shadow casting off, because it would completely change the visual, right? But you can think of others where the visual impact was minor and we were able to disable that shadow casting. All right, so now probably the most important part in the reduction pipeline was the mesh optimization. This is what helped us reduce the overall memory load and improve both GPU and CPU performance significantly. So what you need to know about this is that this manifested in a few ways, but the general mesh improvements, but this mesh optimization is the main part that I'll be talking about here. And this is an automatic process that we created. So most of these meshes were optimized automatically. It's a headless process that runs during the reduction pipeline, and it's also deterministic. So if you don't know what that means, essentially, every time we run this process, if the parameters stay the same, the optimization parameters stay the same, the result was the same mesh with the same indexes, and all the mesh information was the same every time. And this result was also incremental. So what that allowed us to do, or cacheable, because it allowed us to be able to run only parts of the reduction pipeline and count that the meshes were always the same, right? Because it was deterministic. And ultimately, you can think of it as a simple mesh decimation process. It takes a mesh as an input. It outputs a lower vertex count mesh. And I'll be showing you a before and after here, so I'll get out of the way here. This is a giant mountainside in the starting village in Timberheart, if you're familiar with the game. And after an optimized version of that, so I'll be going before and after a few times, significantly reduced the poly count. I believe this was about 20% of the original. And the benefit here is that we did this without changing the gameplay, right? The player could still climb and fly, not climb, use the jetpack to get to those areas, and the collision was almost identical to what it was originally, but with far fewer resources. All right, mesh splitting and mesh combining. So overall goal here was to reduce the size of some meshes and increase the size of others. So essentially, if a mesh is too large, it will always be seen by the culling system, by the occlusion system that Gus will be talking about in a second. So think about it like if it's just too big, the camera will always see it. On the other hand, if it's too small, we'll be sending thousands and thousands of meshes to the GPU to render, right? So that's less than ideal as well. So we tried to find a compromise solution to create what I like to call appropriately sized meshes. So the two examples here are, one, we split very large meshes, and this was all done automatically based on certain sizes. So we split very large meshes into chunks that were about house-sized. So you can, there's some room there, but essentially think about a house-sized object. So that one, the giant piece of the planet, was split into 3, and then the opposite, combining very small meshes into larger meshes. So in this case, props in the village such as barrels and planks and the stairs, were combined based on material. So this was also important because it still allowed for batching, into just larger and fewer pieces. And essentially, this was something really important to the calling system because it had to deal with more appropriate size and also fewer meshes. Another step, and probably the most painful one from an artistic point of view, if you will, was content removal. So we reached a point towards the end of the project where we were very close to hitting all our performance benchmarks, but we just needed that last squeeze. And what we noticed was that there were several props that were meant to just create visual clutter and essentially make the player feel like that world exists and belongs. So what we tried to do is analyze and understand the distribution of props throughout the game. So this was, again, more of an artistic process than a mechanical one, if you will. And we tried to identify areas of significant repetition. And then beyond that, we also really needed to understand the artistic and game design intent. So then most importantly, what we did is we worked with the Mobius art and design team, and through a process of continuous iteration, we started removing some of the props that were just there to create this feeling of clutter without really impacting the game. And we're talking probably about a few hundreds across the game, but ultimately it just reduced enough of the renderer count for our CPU performance to be where it needed to be. And again, very important, we provided the Mobius team with tools to toggle this on and off so they can make an informed design decision of whether that compromises the vision of the game. And we reached a point where we both felt like it didn't compromise the game and it still maintained the identity while improving that performance that we needed. So I have an example here of a scene where we remove, if you see, I'll go back and forth a few times, a few of the broken pots and other pieces around disappear. That's because those are removed. But those are all high enough up that the player might not see them anyway to begin with, right? And there's still enough left to create the same emotion and the same storytelling beats. Okay, and last but not least, I want to talk to you about one of my favorite parts, the LODs and the HLODs that we did. So our objective here, ironically, actually, was to improve CPU performance. This was added at a point in the game where our GPU performance in most places was very stable and consistent and good. However, we still were, one of the biggest bottlenecks on the CPU was just that we were still sending too many meshes through the CPU to the GPU. So what we tried to do was actually to use LODs to replace a large amount of meshes with a single mesh, which especially at a distance was something that reduced the overall renderer count, right? So the LODs we created, they're both some automatic, some manual. And if you're asking why, well, for example, most automatic solutions don't deal really well with bevels, for example. So things like the houses were some of the things that we optimized with using manual techniques with our amazing artists. And some things were optimized automatically, like some of the cliff faces you've seen and other many props, terrain, and things like that. Overall, the main goal, like I said, was to reduce the renderer count. And then we also created HLODs. So this is not necessarily your typical traditional HLOD, but instead we took an idea that the Mobius team had already implemented, this idea of a proxy, which essentially represented a simplified version of an area. So what we added to that is we took some of the LODs that we had built and combined them into a mega LOD, essentially, and optimized that. And essentially this worked hierarchically on a set of LODs to, the further you were, it would swap to this mega LOD or HLOD, as we were calling it, and replaced an entire proxy, an entire area. Adding these LODs and HLODs also, as I mentioned, drastically reduced the vertex count in the scene, right, which helped the GPU tremendously. And it was an immediate benefit to the occlusion system. And I'll let Gus tell you more about that.
Right. So, as I had mentioned earlier, we weren't able to use any of the out-of-the-box occlusion systems that exist. Most, if not all, rely on static occlusion data to process occlusion. So we needed a solution that could be dynamic, repeatable, and be efficient within Outer Wilds. So let's go over what we sort of implemented. The idea that we landed on was to identify data that could be relative to an origin point. The most common case was using a planet's center as the origin for all of the objects on that planet. For example, a tree on Timberhearth, the home planet, isn't going to move relative to the planet itself. So we ended up baking the data based on those origins. And it allowed us to have static data without having to churn and do a bunch of calculations to keep data updated. And it also allowed the planets to move without much work from us. All right, so what did we actually end up using as our occlusion targets, our OCLUDs? Many things. So basically anything that was static, that didn't move relative to the planet, and anything that we could adjust their rendering modes for. This included things like renderers, of course, lights, animators, skin mesh renderers, particles, LOD groups, and anything that had maybe an intended state that we needed to keep track of. And we also implemented a way to register state changes across the game so that as the player interacted with objects, their state would remain as intended. So if a player turned off a light, it would stay off. And one of the things that we implemented for Outer Wilds was this idea of occlusion levels. In this example, I'll just give a quick example. For a renderer here, we had the concept of a renderer being visible, as you see here, softly culled or occluded, where the player might not see the object directly, but we might need to have something running for that object, such as a shadow. And then hard culling, where we disable the object entirely. This was very useful for us for being able to iterate in the occlusion system to fix bugs and adjust behaviors of individual objects according to their design. We weren't sure exactly what we knew that we wanted to work closely with Mobius Digital and Annapurna to make sure that the game stayed true to its vision, and this helped us do that. And off to the occlusion techniques. These are the methods we use to decide whether objects are to be occlude, what objects would be occlude, and how. Many of these techniques were used. These techniques were used to provide improvements to the CPU performance and to the GPU performance, not just for rendering, but also other general CPU costs like animators. But before I continue, I wanted to note that these techniques worked best in tandem. That is to say that they worked best when they worked with each other, depending on the situation. Because all of the planets were quite unique and presented different challenges. For example, one planet where a player might be traversing the insides, one technique may not work well for that situation, while that same technique would work well on a different planet. And I'll give examples as we talk through them. So the first technique is very common. It's the frustum culling. For anybody who doesn't know what frustum culling is, it is simply anything outside the camera's view gets excluded from rendering. In this example, we see the player near the center of the planet looking around, and you can see the effect that frustum culling has on this planet. The second technique that we used was a distinct version of distance culling. Normally, the frustum culling would handle this, but in Outer Wilds, you're playing inside of a solar system, which means the frustum far plane needs to be very far away from you. So we couldn't use that. Instead, we used a combination of a arbitrary distance from the player and the size of individual objects to determine whether or not they would be culled. This allowed the system to cull out small objects much earlier than larger objects, because we still want to be able to see planet-sized pieces of geometry from far away. In this example, we're on a DLC planet where you can see straight across completely. The player is zooming in on an area, and you can see the trees come into view and out of view. The third system that we implemented is shapes and portals. It's much like the Unity occlusion areas and portals. Essentially, we designate an area, like this in blue. Anything within that area is then associated to that space. And when the player moves around this if the player is either inside the space or inside of one of these yellow portals, the objects inside of the space become visible. But if the player is not in any of those, they become cold. Ooh, this is one of our more creative techniques. This was a LOD-dependent culling. One thing that Raz didn't mention earlier was that when going through the asset processing pipeline, yes, is that what we're calling it? Yeah. When we were going through that process, there were objects that nearby LODs that would get tagged. Smaller objects that we could cull out at different distance that would become associated with different levels of the LOD, which allowed the occlusion system to then cull those objects when those LOD transitions happened. In this example, we have a building. Inside that building, there's a bunch of museum pieces. As the player moves closer to that museum building, the objects become visible. But when the player moves away and the LOD transitions to a lower level of detail, the objects inside of the building become occluded. And lastly, my favorite technique, because this was a fun one to discover, we found early in development that an issue where the player would presumably look down at the planet often, and we noticed in GPU profiles that the opposite side of the planet was being rendered, even though the player is not going to be able to see that, right? So we came up with a little calculation to determine the horizon on a spherical planet to determine what the player can actually see. In this example, the player is up on the moon there, looking down on the planet, and we can see a bunch of renders being disabled based on that. And as the planet moves, the disabled renders also change. Now, as the player would move closer to the planet, more of that opposite side of the planet would be culled. Right.
All right, so now that we talked about the two major systems, let's talk a bit about the one-off optimizations that we did that couldn't fit in those two buckets, but were still incredibly vital to improving the performance of the game. The first one I want to talk about is dynamic resolution. So essentially, if you're not familiar with this, dynamic resolution is a performance scaling technique that allows you to take the previous frame's GPU timings, or typically the last couple of frames, on average of those GPU timings, and decide if you want to lower the renderer's output resolution to improve the FPS. So this also allows you to set minimums, right, to that resolution, and then the system will do its best that it can to reach that FPS while not going lower than the output resolution that you desired. We implemented this in the game because it benefited areas of heavy GPU usage. For example, the core of Brittle Hollow, we were required to draw almost the entirety of the planet when you're inside the planet. So that benefited tremendously from this technique. At the same time, we didn't apply this to UI, for example, for two reasons. One, the UI performance was already very good at this point. And at the same time, we didn't want to lose the crispness of the UI, something that the player would notice much easier or much clearer than it would on the environment. One awesome thing about this is that while we had to implement this solution in the built-in render pipeline in Unity 2019, Unity 6 has, in all of the render pipelines, has this ability built in. So you can use this straight out of the box. I'll pass it back to Gus to talk about asset streaming.
Yeah. A big thing that we did to improve memory in Outer Wilds was simply to increase the number of assets that would be streamed in on individual planets. This lowered our baseline memory usage across the board. So it freed up a ton of memory for each planet to be able to load in their own assets or increase the number of assets loaded on each planet. We also moved anything we found in the resources folder over to an addressables bundle, which allowed us to better control what was in memory from resources. Again, lowering our base level memory usage. And the last bit the last bit we did for asset streaming was implement a concept of asset load prioritization for our asset streaming system. Asset load prioritization is simply put was a list of prioritized meshes in an asset bundle that would get loaded in before anything else. This made it much easier to maintain the player experience. And the best example of this is fast warp pads, where a player would get teleported from one planet to another. And in those cases, the streaming system would dump the entirety of assets on one planet and start loading in from the new one. It was critically important that we load in certain assets immediately when doing that, because you only have 1 or 2 seconds to do that when the player moves. Retaining the player experience when they land on the new planet without revealing that we are streaming in an entire planet, A couple of other optimizations that we really wanted to make sure we talked about were the audio management. Audio management is more important than you might think. 1 or 2 audio sources that are enabled may not make a big difference to CPU performance, but a great many will, because there is an overhead to keeping those enabled. So if you don't have a need for an audio source to be enabled, please disable them. Another thing that we heavily used was system burstification. That is using the job system and burst compiler to optimize your systems. We did this with the audio management systems we implemented and the occlusion system. And of course, we also added this to a Mobius implementation, a system. They referred to it as a shape system, which was prime for burstification, which actually improved our fixed update significantly. And finally, enabling streaming textures and bitmaps helped us immensely, just to maintain a strict texture memory. All right.
All right, so let's start wrapping up things here. We're going to talk a bit about the conclusions. So how did the systems that we built address the challenges that we started with? Well, it's important to know that every single thing we did had a target, right? And ultimately, the benefit of each of the implementations was systemic. It wasn't just for one piece. So as mentioned in the beginning, we had 3 major bottlenecks, right? The memory, the GPU performance, and the CPU performance. And as you see listed there, some of the systems that we built targeted specific things. But what you see in this Venn diagram is actually, the story is somewhere in between, because different systems impacted multiple things, most of them in good ways, but some were calculated decisions that maybe decreased CPU performance, but improved GPU performance significantly, right? Or the other way around, maybe we paid a bit extra memory cost, like for LODs. Most LODs were low poly meshes anyway, but they added to the memory usage. However, they tremendously improved GPU performance. And actually, if we were to be honest, that would belong in the middle because it actually improved CPU performance as well. There are fewer renderers on screen. But we tried to show what it mainly impacted. So I'm not going to go for each one of these, but essentially you'll see that every single optimization impacted multiple areas of performance. Mesh optimization, for example, was primarily done to improve memory, to reduce the amount of memory that we had to load for the assets, but it improved GPU performance as well. Particle optimization, again, targeted GPU, but improved CPU as well. In any case, the important note here is that every single system had a major systemic impact, if you will.
Right, so now that we've talked about performance, just want to quickly say Outer Wilds is available now on the Nintendo Switch, both digitally and physically. And we've shipped 5 patches out since release back in December. Each time improving the player experience and fixing bugs and just increasing performance here and there. Of course, not all improvements made it in, but the developers of Outer Wilds and us, we'll be taking the things we learned from the project and applying them to future endeavors.
All right, so before you run out and buy the game, here's a few takeaways from today. As a recap, instead of summarizing every single step that we did and what the gains were, I want to kind of talk about some general takeaways. For example, these are some optimizations that are almost always a good idea. So try to optimize your biggest bottleneck first. The idea behind this is that often the biggest bottleneck occludes some of the either hidden smaller problems, right? Another one is to just try to draw fewer things, right? Whether that's making sure you have a calling or occlusion system that just eliminates renderers from even showing up to the camera, or that you implement solutions such as LODs or HLODs to just reduce what the camera sees. Another one is to distribute the CPU efforts on multiple cores, so you could take advantage of jobs and the burst compiler to do that. And also to consider that not all lights need to cast shadows. And as a corollary to that, if you will, not all objects need to cast shadows. So you can have a situation where that bright light, for example, that's on me right now, that needs to cast shadow, so my shadow is being cast because anyone would notice if that wasn't the case. However, my favorite example is if you have small assets like small pebbles on the floor, those might not need to cast shadows because having them cast shadows will probably not make a big visual impact anyway. So those are areas where you can, last minute try to reduce the performance implications. And then, like I mentioned, things like dynamic resolution, almost always a good idea. It has some CPU impact, but the benefits on the GPU are usually outweigh that. And again, one of the great things about that is, unlike us, you can have all this built in by default, and you would just have to implement it in your own project.
All right. Just before we leave, a little premature. But yeah, before we leave, we just want to say a great big thank you to Mobius Digital and Annapurna Interactive. They built a wonderful game, and their dedication and passion of the game greatly inspired us to push ourselves to deliver the best version of the game that we could for the Nintendo Switch. So great big thank you to them.
And I also wanted to thank everyone at Unity who helped us through this endeavor. We had over 20 developers, some for just a few days, offering their expertise, and some for many, many months. And we are just a sliver of the team that helped bring this project to life. So again, I wanted to thank them all. And last but not least, we wanted to thank you all for being here and watching our presentation. And we hope you enjoyed it.